Hello, everyone, and welcome. Thank you so much for joining us here today at our latest KNOWR webinar, Repair versus Replace, Navigating the Critical Choice After Electric Motor Failure. My name is Jamie Lancaster, and I'll be kicking us off today. We're really excited to have you here, whether you're joining us from a maintenance team, facility management, or operations. This topic is one that affects all of us when critical equipment goes down. Before we dive in, just a few quick housekeeping items. Today's webinar will run approximately 45 to 60 minutes, and that includes time for a Q&A at the end. We'd encourage you all to use the Q&A feature in Teams throughout the presentation. No need to wait until the end. You can go ahead and submit your questions as they come to you. And now I will introduce our speaker for the day. We're fortunate to have Stephen Carbone with us today. Stephen is the president of Industrial Electromechanics, and he brings extensive expertise in electric motor reliability and testing. He holds certifications in field dynamic balancing and vibration analysis, and has been a member of the EASA Technical Education Committee since 2021. At IEM, Stephen leads a team that manages the repair, rewinding, and machining of critical motors, generators, and pumps for industrial facilities. His entire career has been dedicated to helping operations like yours optimize asset life through high-quality maintenance and data-driven reliability strategies, which is exactly what we need when facing that critical repair or replace decision. So, Stephen, thank you so much for being here today. I'm going to go ahead and turn it over to you now.
All right, awesome. Thank you, Jamie. I appreciate it. Good afternoon, everybody, and good morning to those on the West Coast. I appreciate the opportunity to give a little insight into what I consider a critical choice after an electric motor fails, and that's repair and replace and making the best decision. I hope to go over some of those points right now and give you guys some help with your day-to-day maintenance decisions. So I'll go ahead and get this kicked off. Just to introduce a couple aspects of the businesses associated with this. The KNOWR Network is a group that we're a part of as my company being a founding member, and it's made up of 6 independent organizations. Majority of the ownership is multi-generational, which is fantastic in this industry, and I know a lot of people appreciate that service of an independent organization. And we span across the entire United States with over 20 locations. So it's a great group to be in. If you are in the area of a KNOWR member, you're going to get consistent service across all facilities and all locations. So it's a great group to be a part of. Just a quick introduction into my business, and we've been operating since 1995 in Garden City, Georgia, which is just outside of Savannah, Georgia. We specialize in the repair of electric motors, gearboxes, pumps, and generators. We offer a wide range of field service capabilities. Our focus is on reliability and service, and we also sell a significant quantity of new products. So really this presentation goes into a lot of components of the business on the repair shop and new product side of things. This is also a presentation that is a component of our 6 keys to maximizing reliability of rotating equipment. This is a foundational process that most KNOWR members follow, and this is going to be within the specification section. So really good information and really good assessment for you to understand if your organization is healthy through all 6 of these key components to maintain and maximize reliability of your rotating equipment. All right, to get into the repair and replace decision, I'm sure everybody's been a part of the high stakes failure when the phone rings on a Friday afternoon and you get the call that a piece of equipment of yours has failed. I know this has happened plenty of times, sometimes on holidays, sometimes on in the middle of the night, but yeah, you always get that phone call when you don't want it. There's going to be a lot of pressure, when this motor fails as to what you want to do. So really I want to give you a roadmap and an understanding of what the best process is to make the right decisions from a long-term asset health standpoint. So rather than make any rash decisions and making shortcuts just to get something up and running, sometimes you need to, but sometimes you don't. So it's important that you see all the data, you see all the options, and you understand what is the best decision for your facility. how do we go from a reactive state to a proactive state? So number one, you don't get those unplanned calls on a Friday afternoon, and you're able to start really having a structure for your maintenance program that allows you to be proactive and make some of these decisions that we're going to talk about today. So one thing, that's been in the industry for a long time is this percentage rule. So 50% of repair versus replacement, you would go ahead and replace, or 65%, 60%, whatever the cutoff is. But we really need to get past this percentage rule. It does not work from a long-term reliability standpoint, and it does not necessarily achieve financial goals for some of the things that I'm going to get into today. The theory behind this is the iceberg theory, which is really looking at total cost of ownership. You can see over there in the iceberg, you can see the price, it's right in front of you, but then all of those costs are underneath that are a little bit harder to capture sometimes. And that comes to maintenance costs and energy costs, different things that I'll highlight shortly. But it's really important, to make the decision for total cost of ownership. That depends. It's not just necessarily the dollar amount that's coming into play there on that initial purchase price. So really important that we're thinking, more from a data driven standpoint, more from an analytical standpoint versus just the price of the item initially. So I'll be going through 4 sections of this. This is typically going to come up in every single repair versus replace decision. Anytime an asset fails, you're going to need to really go through these steps and understand, what is the information from each one, so you can make that good final decision. So we'll start with the financial review. We'll get into a technical assessment on the asset, what failed, how did it fail. We'll get into what data you should expect from your vendor. And we're going to be looking into the root cause failure analysis decision to make sure you are repairing something correctly, replacing something correctly, or making some modifications with that insight that you get into that RCFA data. So starting with the first, we'll go into the financial review. This is where we start looking at total cost of ownership. It's important to note that electrical consumption is by far this most significant component of operating an electric motor. So I've seen different numbers, anywhere between 90 to 97% of the cost of an electric motor is associated with its lifetime energy cost. So you can see that the purchase price is a very small percentage, and the maintenance price is a very small percentage compared to the total energy cost of operating these electric motors on, quite often a 24/7 basis, or, maybe that minus a couple weeks a year for an outage. But, the main focus of our topic would be, the heavy industrial continuous duty motors that cost a lot to operate. So repair and replacement should absolutely prioritize efficiency. Okay, that's ensuring that you have an efficient motor that you're replacing it with, or that you have a high quality repair that's been performed to industry standards and allows you to ensure that the efficiency has been maintained during that repair process. So, a couple of percentages up or down can make a significant change on your energy costs. So it's really important that we're looking at the details during that repair process. There's a lot of industry standards out there. A lot of customers have their own. During this presentation, I'm not really going to go into really specific details on specifications, because everybody does have so many different ones. But ESA puts out a really good practice to maintain motor efficiency. At the end of the presentation, I'll have a slide that gives you some resources on where you can go for learning about that, and what is a part of the to efficiently to rebuild a motor from the highest level of efficiency. All right, so let's talk about efficiency standards real quick. There's been a lot of changes over the years, as you can see. These standards are all associated with 600-volt machines and less. So a lot of people have medium voltage machines out there. This is not a type of machine that is mandated from the Department of Energy standpoint. but most motor manufacturers do follow the efficiency standards that they set forth uh, for both low voltage and the medium voltage product. Um, Super premium efficiency is starting in June of 2027. That's come out. This is following the IE4 European efficiency standards that came out a couple of years ago. So they are going to start mandating that in the United States starting June 2027, and that'll be based on the 100 to 250 horsepower T-frame rating. So be on the lookout for something coming out in the near future with motor manufacturers changing designs and continuing to drive towards a high level of efficiency. Over the years, you can see that the history of motor efficiency has increased over the years. I thought it was also interesting for doing a little bit of a history lesson that we actually did have a little bit of a dip in average efficiencies, and this was put out by the Department of Energy. You can see that, back in the day during 1940, 1960s, going into the 80s, these motors were really well built. I know everybody can kind of relate to that with a lot of, you know, pieces of equipment that were built back in the day, and things just aren't built like they used to be, is a common saying. So back in the day, we had a lot of efficiency out of these older style motors just because they were overbuilt workhorses. They had a lot of iron, they had a lot of copper in them, which resulted in a higher level of efficiency. Now, in the 80s into the early 90s, we had a little bit of a dip in efficiencies, and that's when motor manufacturers started going to the optimized T-frame motor. So, prior to that, in the 40s, 50s, and 60s, there was a lot of U-frame motors out there, pretty much all U-frame motors. There's still some that are in operation today. But they did start as energy costs started to increase. They were continuing to look for ways to make things more efficient, and they started going to the T-frame style motor, which is what we use today, like a 449T or a 254 T-frame motor. There was a little bit of a learning curve as they started designing these motors, so we did have a little bit of a dip in the late 80s, early 90s. With efficiency, but the motor manufacturers did start optimizing these designs and came up with new material, and were able to start increasing the efficiency levels of these new optimized motors. And in the early 90s is when the Department of Energy started mandating these efficiency levels. So you can see they've continued to push forward. So little history information, good to know information, and I thought that was interesting with that dip, but now an increased level of efficiency. So when you're talking about efficiency, one of the major things that we're looking at, obviously the operational cost of a motor from an energy consumption standpoint is so high. We're looking at a difference in efficiency levels from a 1995 motor, a standard efficient motor, or E-Pact efficient motor, and comparing it to a premium efficient motor. So there's a handful of formulas out there, but I thought this one was a relatively simple one that you can do in a quick fashion without knowing a ton of data. But this is a combination of mostly Department of Energy paybacks here, where you have your annual energy savings on the top left. This would be your difference between a higher efficient motor and a less efficient motor. We're going to be plugging in things like hours of runtime and your electrical utility rate. You're going to look at your annual operating cost based on that information, and then what would your payback be? So price of a new motor minus the cost of repair, and then your annual energy savings will give you that payback. So we're just looking at a scenario here. We've got a 200 horsepower motor failure. It runs about 8,000 hours per year. 24/7, 365 is 8,760 hours. So this one's running just a little bit less than constant. And then we have a 10% per kilowatt hour energy cost assumption. So that can vary widely depending on where your facility is located, where if you generate your own power, if you buy your power. So it's definitely something that you need to look into, and most folks know at their facility what their energy cost is. So you would just plug that in for whichever is applicable for you. Um, Looking at the repair costs, we're looking at $4,000 with the existing motor having an efficiency level of 93%. And then the replacement cost is 12,000, which is higher than repair. But this is a motor that is premium efficient at 96%. So, you can go through the calculation here. We've got our 93% versus 96%, 10 cents kilowatt hour energy cost assumed, and then 8,000 hours running. We're looking at a $4,000 savings per year for the replacement motor versus the new motor, versus the repaired motor. So, calculated payback, you're looking at about 2 years. Obviously, this is a pretty good return on investment for this particular motor. For these lower cost NEMA T-frame motors that are typically, a lot would be considered throwaway. These are kind of no-brainer decisions. You do start getting into more complex decisions when you get into lead time and the overall purchase price of some of these larger medium voltage machines. But a lot of these low voltage, if you're coming into it and you have a less efficient motor that maybe was EPAC rated, it's a pretty good decision to go ahead and replace those because you're going to gain the money quite fast on a return on investment. Something that gets into a little bit more of a complex scenario is when you're looking at what your actual efficiency is. So it's important to note out, I'm not going to really go into detail on this topic, but it's important to note that efficiency levels are going to vary depending on the application, depending on the percent the motor is loaded at. You have, things that could change from the original design of this motor. So voltage supply can impact your energy efficiency. So the Department of Energy does have a little bit more of I guess, a more thorough calculation to actually understand what is your true efficiency and what is your actual kilowatts that you're using. So take a look at that. I give it later on in the presentation as a reference point, but it's very important that the true efficiency is known. Just because it says 95% on the nameplate does not mean that your application is actually gaining 95% efficiency depending on how much it's loaded, especially if you're going 50% or lower. Efficiency is really going to drop quickly for an electric motor. So getting into the technical assessment, so you've had this motor fail. Now you need to understand, is it repairable and can it be rebuilt to maintain a high level of reliability and to maintain a high level of efficiency. So you can definitely crash a motor. We've seen it plenty of times here in our repair shop where there can really be a lot of damage, and understanding and working with your vendor is something that can help you assess if this is something that can be achieved and be repaired to like new condition, and maintaining everything that was originally designed, and can it be built better. So just a highlight of some of these particular components of this failure. This is a pretty common occurrence where the drive-in bearing has failed, whether it be due to lack of lubrication or a misalignment issue. We've had a drive-in bearing failure. This bearing has failed. It has dropped. The rotor has made contact with the stator, and you've had both rotor lamination damage and stator lamination damage. So it's important that you can see it, and you can work with your vendors to understand. Is this something that can be repaired? Is this going to be a problem and generate some issues with reliability and or efficiency? Are these definitely big red flags that you want to look out for? We're kind of going into one of the issues that could occur in that last slide is the laminations, and can it pass a core loss test? Even before that, if you don't have lamination damage, you want to make sure that these motors are burned out properly in a controlled oven. So you can see on my right here, we've got a open flame that cannot regulate the temperature properly. So you never want to see that. You need to expect that your repair vendors have, adequate equipment to burn out your motors in order for them to remove those windings and prepare that core for a new winding. So, make sure we've got a quality oven. A lot of companies, a lot of customers of ours at least require data logging of that temperature just to make sure this core is not being damaged, because one of the big things you're looking for is a less than 700 degree Fahrenheit oven temperature while this motor is being burned out. Some customers have tighter specs than this, but ESA currently publishes it as less than 700 degrees Fahrenheit. They have proven does not create any lamination damage and is able to maintain the efficiency of the particular motor. When the motor is burned out, you then need to remove the winding. So it's important that it's done carefully and that none of the laminations are being distorted, the motor frame is not being distorted, and that no laminations are kind of mushrooming out. So you really want to make sure that the core integrity from a physical standpoint is left in the best possible care. So you don't want somebody ripping coils out and causing all the laminations to start moving. So really important that attention is paid during that process. And then core loss testing before and after. So core loss is a absolutely important aspect of the burnout process. You need to know what it was before it was burned out and what it's going to be and what the results of it are after it's been burned out. So typically you're going to be looking for a core loss increase of no more than 20%. This can vary also, but you don't want a significant change. If you have a significant change between the before and the after, you know that that temperature of the oven was either too high, that it spiked, or other reasons that could cause that core loss test to fail. But without a good core, without good lamination insulation, you're going to start developing shorts, and that's going to show up in your core loss test. You also want to make sure that hot spots are less than 10 degrees Celsius difference from ambient temperature of the laminations themselves. So hot spots are going to generate, heat, which is going to generate losses, which is going to generate insulation failure, and all sorts of things kind of cascading from there and snowballing from there. So you don't want any hot spots, and you want to make sure that you're getting that data and you understand that your core is good, or you're going to continue to have reliability issues and continue to have a reduction in efficiency if these aren't checked properly. Yeah, now the nice thing about the repair process is that you can look for upgrade opportunities and be able to make the motor better than it was originally designed. So, assuming all the care and attention has been performed on the motor up until the burnout process, you can then start looking at ways to improve it. This adds a lot of value. This is where you partner with your motor repair company to make sure they're looking for any opportunity that can benefit you when that motor's in service. So we're looking at potential installation class increases. We're looking at as to whether or not, if the motor is on a VFD, does it have the appropriate insulation for that on the magnet wire? You can also see some scenarios where VFDs cause a capacitance issue with the voltage that may need additional turn-to-turn insulation added to it. So these are things that you want to be looking out for. Has it been VPI before? Can it be VPI now to get a better insulation throughout the winding system? Standard versus ceramic bearings, that's an opportunity for motors operating on a VFD that may be susceptible to electrical fluting. Improved enclosure sealant. So, depending on how the motor was specified when it was originally purchased, it could have been a IP55 motor, and you may be able to add some sealant and give it an opportunity to be an IP56 motor. Really important, especially in our part of the world here in the southeastern United States. Very humid, a lot of rain during the summer. So, making sure that those enclosures are sealed as best possible from a rabbit fit standpoint is critical. Bearing isolators, again, the motor may not have had it when it was originally specified and purchased, but you can add labyrinth type seals to prevent any sort of moisture or contamination getting into those bearings while it's operating. Grounding brushes, again, another VFD operated motor benefit is making sure that the stray shaft currents are going to ground appropriately. Improved rotor balance. So it really, again, it depends on how the motor was originally specified, but it may not have a rotor balance that would be the best for lowest levels of vibration. So motor repair shop can improve that rotor balance from what it was at the factory. And then improved cooling and enclosure. So this usually takes some engineering, but it's definitely an opportunity to improve the motor. If you've changed the application over the years, things like that, where you can get more air over it, or you can improve the enclosure for an area where there's been an increase in moisture, for various reasons. So a lot of opportunity on the repair side to create upgrades, and that's a big component of this, where it can be built better than new in some scenarios, and having that relationship with the repair shop to work through those is critical. All right, so vendor data. This is your relationship with your vendor, so it's important that you have an open line of communication both ways, so that you understand what they need and they understand what you need. So, just to kind of specify, go into the specifics a little bit, is going to be the repair proposal stage. So they've done their whole inspection, they've dismantled everything, they've now presented you with a quote. So, just some highlights of what you need from your repair vendor so you can make this appropriate repair versus replace decision is critical. It's critical that it's sent to you in an organized fashion, and that we're getting all these boxes checked here down below. So with detailed work scope, obviously we don't want to just say motor repair. What is the repair that's being performed, to give you that insight as we're going into our kind of asset qualification. Can it be rebuilt to like new? Understanding what that work scope is. How are they doing some of the machine work? How are they doing some of the types of shaft repair, and ensuring that it meets your specifications? You've got an inspection report that is going to highlight damaged components with pictures. Some customers want all the pictures, some just want to see what is out of the ordinary. But it's very important. Pictures tell 1,000 words, and the more pictures, the better. Those are usually pretty easy to take care of during the teardown process. So making sure that you get those pictures, that you understand what are those pictures showing, is critical. And that gets into the work scope, where these are, somewhat of a justification of that repair work scope. Cause of failure, I'll get into it in the next slide, but it's critical that you understand what caused the motor to fail and how can you prevent that moving forward. Core loss test results, making sure that the core loss has been performed. A lot of folks trust the repair vendors, so understanding that they did it, and if there are any questions, that there's conversations that happen again, and ensuring everybody's on the same page. But making sure that these core loss test results are acceptable is critical. Going into some of these improvement opportunities, as I stated on the last slide, is what features are being quoted for reliability improvement. So, did the repair shop notice that there was contamination in the grease? If they did, the expectation would be that labyrinth seals being quoted with this new repair that's coming through. So, really just making sure that everybody's working together to keep these motors running in service as long as possible. Some of the things we'll see, at least in my shop, are observations where we can help the customers really understand how are their maintenance practices and how can they get better. So if we're going to see something with a lack of lubrication, that's usually pretty easy to tell on a bearing. We want to convey that information. So what can be done on the customer end in the future to improve reliability? Just because it's a motor failure doesn't mean it's the motor's fault. So really understanding that. Of course, the price of repair and the lead time of that repair And then the replacement motor cost and lead time. So this is where you start weighing your options. There's a lot of things that come into play, especially if it's an emergency situation. How long do you have to get the motor back? Should you be replacing this motor? And these are all levers that you can start pulling. And I'll get into a decision tree shortly to really kind of see how you go through that process. But understanding the cost and understanding the lead times, must be given every time, and having that replacement motor as an option every time. And then just another point of data to help you make some of these calculations on return on investment are the efficiency of the existing motor that's in for repair and the efficiency of the replacement motor. So, it's usually going to be a higher level of efficiency with the replacement or the same level of efficiency. Very important that you have that information. Again, have it in an organized fashion so you can take a look at it and understand what needs to be done to make the right decision. All right, so yeah, root cause failure analysis, critical component of the motor repair process. We don't want to band-aid anything. We don't want to cause a reoccurring failure if it wasn't analyzed properly when it was in the repair shop. This also helps you understand, is it a motor issue or an application issue? And do we need a different motor or do we need a better motor? Now, this better motor can be through the purchase of new or the repair. But it's really important that you start looking at these aspects of the root cause failure analysis to understand what needs to be done next. So in my picture here on the right side of the screen, I've got a bearing that has some pretty obvious signs of electrical fluting in it. Doesn't matter what you repair, doesn't matter what you replace it with. If you put a motor lacking bearing protection in that spot, it's going to fail again. So really driving in and understanding what was the cause of the failure, how do we prevent it, or we're just going to keep necessarily just throwing good money at a bad problem. That's the last thing we want to do. System issues. So don't overlook these also. Over the years, production changes, operations changes. It's always a continuous push to get more out of an existing system. So it really needs to kind of have that holistic approach to look and see, has anything changed with the process that may cause a motor to need to be replaced with something else, to be repaired differently, or in order for it to run reliably, that particular system needs to go back within design criteria. So, none of this matters from a repair versus replace situation if the system is going to continue causing it to fail. So, the couple examples of this: production design changes. Like I mentioned, we're trying to push this machine further and further past its design curve. You're going to constantly have issues with the electric motors and the other equipment that the motor is driving due to heat and wear and things like that. Structural degradation, we've got a lot of it. Again, we've got some older facilities here in our area where foundations are starting to fail, and you've got cracked bases, things like that. So that's going to start really impacting the reliability of this particular piece of equipment. Power quality is a big one, as I mentioned. From an efficiency standpoint, the power quality is critical to understand how true your efficiency is for that particular item. So not having appropriate power quality is really going to start skewing your efficiency and start driving up your operation costs. And then poor installation. This should be able to be seen when you're looking at a motor failure and getting this report from your vendor. But if it's not installed properly, of course it's going to fail again, and understanding that and having a better plan on how to install it is critical. So again, going back to that Friday afternoon call where everybody might be ready to go home, but it's important that the steps aren't skipped and that you continue to make good decisions for long-term reliability, for the lowest cost of total ownership, total cost of ownership, and make sure that each step's being done properly. So some of these final thoughts that we've got here, just kind of wrapping everything up a little bit. Have a decision tree. This is really helpful. This is going to help create a formal process. This can obviously be shared via email or printed out and posted in a different particular facility or storeroom or wherever that it is best located. But have this so it can be followed consistently. You know, we've gone through a handful of topics. They are relatively simple, but you want consistency across the process, no matter who's doing it, what department's doing it. You know, there's a lot of turnover nowadays from an employee standpoint. So making sure this process continues, you know, down the correct path and that steps aren't being skipped during this. So, you know, just to kind of run through it, this is something that you can create based on the expectations at your facility and how you know, how do you feel is, you know, what do you feel is the most important aspects of the process? But this is really hitting, you know, all the high points that we're looking at here. And, you know, we've got a failed motor starting off. Is the motor suitable for the applications? That's the first one, because no matter what, if you don't get that right, you're gonna have trouble for the rest of it. Understanding that state or core condition. You know, if there was a catastrophic failure, what is the repair option, you know, so you want to make sure that even if it's catastrophic, that you still have the data to understand, do we need to restack the core? Do we need to replace the rotor and different examples like that? Now that may make it cost prohibitive if you do need to start doing some of those significant repairs, but understanding you know, what is the correct way to rebuild this motor to like new condition, and then you can start weighing some of the financial levers and understanding, you know, how does lead time come into play and you know, availability of additional assets. Um, Checking the efficiency, again, understanding, is it a premium efficient motor? If it's not, you probably have an opportunity for some energy cost savings, more than likely. And then running through, you know, is a replacement motor available? Is lead time acceptable? And this can kind of help shape your repair versus replace decision tree. Having a spare strategy is absolute critical also. You know, the best time to make a repair versus replace decision is not during that Friday afternoon call. You know, it's weeks, months, you know, years in advance where you have your spares in the appropriate condition. So you're able to take that failed motor, put it in the spare motor, and take your time and, you know, make the best decisions possible for that particular item that has failed. So ensure your spares inventory follows best practice. It's sufficient for your operations, that you're making the right calls. And then think about, you know, somewhat forward looking also. If we look at that decision tree, you know, the one of the first questions is the motor suitable for the application? So we've got a lot of projects where we are replacing open drip motors and installing totally enclosed fan cooled motors. So if that's an open drip motor in that spot, you know, that does take some work to get that to be able to convert over to a totally enclosed fan cooled motor. So the time to plan is now, rather than having that open drip motor fail because of a moisture issue in the area and those short mean time between failures. But having that open drip motor fail and then not having the time to convert it over to a totally enclosed fan cooled motor is just going to continue being an endless process. So you've got to jump out of the way and make sure that you have a plan in place for some of these assets that may not be specified properly. So just to highlight some of the topics of conversation that I've been going through today, we're looking to try to go from reactive to proactive maintenance here, and a lot of these levers are going to help drive you towards that. So, you know, the repair versus replace decision. Of course, we're having it and wanting it to be driven by total cost of ownership and long-term reliability. So we don't want to be cost focused. Again, we're going back to the iceberg theory where if we're just worried about the purchase price of this item, there's so many other things that can bite you over the years and really drive costs up. So really important that we're looking at this from a holistic standpoint and a total cost of ownership standpoint to achieve the operational goals of your facility. Repair quotes, you need the detailed information so you can make the right decisions and prevent reoccurring failure. And then ensuring your vendors are repairing to industry standards to reduce the chance of any sort of efficiency losses. Again, 90 to 97%, everybody agrees on that number, or the operating costs of your particular motor from an energy standpoint. So if your repairs aren't being performed, if the burnout process isn't being performed, and you're losing 2-3% efficiency on a rewind, that adds up to a lot of dollars over the lifespan of a motor, which is hopefully 15 to 20 years. So again, these motors are very costly to operate, and every percentage counts. So ensuring that you have the right vendors doing the work for you and they are transparent and communication is going both ways is a big aspect of a great relationship. And then some references, if you want to screenshot this, these two organizations, the U.S. Department of Energy and ESA, the Electrical Apparatus Service Association, really go into these topics in a lot of detail. Some of the U.S. Department of Energy documents really give you a framework on how to best proceed with efficiency decisions and understanding, what motors need to be replaced and the justification for those replacements. So take a look at these. These can all be done with a quick Google search. It was very helpful information, and I think it can definitely shape you as you continue to drive for reduced total cost of ownership. And that's what I have. So if anybody has any questions, I'd be happy to answer them.
Yeah, let's go ahead and give folks a minute to type in questions if they have them. I've got a couple that can kick us off.
Okay.
Stephen, back to the payback equation. I was curious, when you're walking your clients through that payback calculation, what number usually surprises them most? Is it that efficiency gap or the annual energy cost?
Yeah, I mean, it's definitely the annual energy cost and how much these motors cost to operate. It really depends on, the kilowatt cost. But, a 200 horsepower motor at 10 cents a kilowatt hour running all year is about $130,000. So, that times that by hundreds of motors at a facility, and those annual operating costs are significant. And it's amazing how much a couple percentage points of efficiency can impact that cost.
Awesome. I've got another one about your decision tree. I felt like it was really practical. And where do you find people most commonly get stuck or make mistakes when they're working through that decision tree?
Yeah, so decision tree, I would say really understanding the true failure modes and what does it take to rebuild something to the like new condition. Making certain that what you're repairing and putting back into service is suitable for long-term reliability. And I think that's a critical aspect. It's easy to know the repair versus replace, dollar amount equation, but truly, what is the repair going to include, and how is that going to help reliability? And then the same thing with the replacement price, making sure that those are apples to apples comparisons, and there's not any differences between the two. The repair price may have more features than that particular replacement price has. So really kind of looking at the features and understanding, where are the opportunities for reliability improvements and driving those decisions.
Awesome, thanks. We have one in the chat. Let's see, I will go ahead and read that out. For 480 volts, what is the lead time for dual winding motor, low speed and high speed? Is industry going away if not using those?
Yeah, so it depends what your application is. So that is definitely more common in the cooling tower industry, and some of those motors are readily available. It really depends. There's a lot of variables when it comes to lead time, but I would say, 10 to 12 weeks is going to be something, relatively common of a lead time for that particular motor, but there are some manufacturers that make those and that they're in stock and ready to go. It's the industry is definitely going away from dual speed motors. With the ability to control the speed through variable frequency drives. So that is more of a dated technology, but there's still plenty of them out there. And but any sort of new installations would be that VFD, which is a another opportunity for energy savings with a VFD being appropriately controlled from a speed standpoint, which is going to vary the load also.
Great question. Thanks. And
Good
thanks, Stephen.
question.
If that's all, Stephen, if folks have questions for you after this, where can they reach you?
Oh, great question, Jamie. Uh, so I've got my last slide up here, which I actually meant to swap to. So you've got my cell phone, my work phone, my email address, and then you can screenshot this thing and pull up my QR code from my LinkedIn. But yeah, feel free to reach out to me with any other questions, and hope this was helpful information, everybody. We didn't get into extreme levels of detail, but it's a good, overall topic of conversation to really start driving change within your facilities. Start with, energy savings and reliability improvements, and really start driving that, within your facility. So yeah, I appreciate the time that everybody gave me today, and hopefully everybody learned something.
Yeah, thank you, everyone. We'll go ahead and get this recording sent out. And yeah, thank you for your time, everyone. Have a good rest of your day.
Awesome. Thank you guys.
Yeah. Bye-bye.